Hello. Thanks, everyone. So, I guess I kind of feel like maybe 50% of what I'm going to tell you today is likely to be wrong. I don't know whether I should tell you which 50% or not. I guess we're sort of interested in interactions between evolution and the Earth system, and how do we integrate what we know about our organisms with what we know about the history of the Earth, or spatial climes, for example, in environment. It's like, start with something that probably definitely is true, and we should all agree about. Some dinosaurs are very big, and actually we tend to become fixated on this point, like dinosaurs are very big. Look how big this dinosaur is. My dinosaur is bigger than yours. Why were dinosaurs so big? I mean, they're interesting questions to ask, but what we actually are often less sort of conscious of is that some mammals are also very big. But actually, we'll find that some mammals, this is a very big mammal. Maybe it weighed 12 tons or so. It might be nearly an order of magnitude smaller than the biggest dinosaurs. So we're really talking about a fundamental different kind of organism. And I think one of the things we might want to address using patterns of dinosaur body size is, do they contain any information about the biology of the organisms? And that's probably the bit that I'll turn out to be wrong about. One of the interesting things about very big mammals is they lived at two specific intervals of the Cenozoic, one of which was during the Oligocene, which is a relatively cold interval compared to adjacent intervals, and that's when you had giant perissodactyls like this animal. And similarly sized gigantic proboscideans lived much more recently, during recent cold intervals, and their patterns of body size, these are plots of body size through time, I should say, patterns of proboscidean body size sort of map onto decreasing climates as you go into the Pleistocene. So it seems like there is some correspondence between the attainment of maximum size in mammals and global climate changes. There also seems to be some correspondence in evolved responses of mammalian lineages in terms of their body size and the spatial distribution of climate. And that's something people often call Bergmann's rule, and people sort of have a lot of semantic discussions about this. But I think the thing I'm most interested in is, if you have an evolutionary tree and you have animals and you know how big they are and you know where they lived and what the climate was like in that place, can you ask the question, do evolutionary changes in body size corresponds to evolutionary changes in the climates that those animals live in? And it seems like with the distribution of living mammals, that is true in general. It's true in large patches of the northern hemisphere and small patches of the southern hemisphere. It actually seems to correspond to a kind of threshold temperatures. So below about 12.5 degrees, mammals do seem to increase in size with decreasing temperature. They don't seem to increase in size with decreasing primary productivity or other things that people might hypothesize could explain size patterns. But as you go to warmer temperatures, actually this is a strange pattern in space that doesn't seem to be reflected in geological time. Then mammalian body sizes seem to have a closer link with the sizes of environments. So there's by no means an unequivocal link between body size patterns and temperature and the biology of animals. These things might vary in space and time. And it's interesting that birds show a similar pattern, but those are endothermic homeotherms. So I have a world that's full of ectothermic poikilotherms today. And their patterns through time are suggestive of very large sizes attained in very warm intervals, which is the opposite of mammals. So this is a gigantic snake called Titanoboa. It's a vertebra of a large living snake. You can see this snake is much bigger. And the story goes that because this animal lived during a very warm interval of the Paleogene, it was able to be very large, even though ectotherms have very slow growth rates. So the hypothesized mechanism for interactions between environmental temperature and ectotherm body size seems to be that ectotherms can grow much faster when it's warmer. And this has actually been scrutinized far less rigorously than patterns in mammals and birds, but there does seem to be a spatial pattern for continental non-aquatic ectotherms today of increasing body size in cool environments, at least within vertebrates. You can see I've qualified this statement many times now, so we actually have a very small number of data points. Really, we're talking about patterns in squamates. But if it is because they're ectotherms, then we might expect to, be able to make some inferences based on interactions between body size evolution and global temperature in the past. So it might be that there's positive scaling of body size with temperature in ectotherms. Now, with dinosaurs, This is a recent sort of figure from a science paper, but people sort of broadly have reiterated this point many times. Dinosaurs are sort of, they're the closest, well, they include birds, which are endothermic homeotherms, and, there's sister taxon of birds living today at least, the crocodiles, which are ectothermic poikilotherms. So dinosaurs are sort of in this grey zone. They're on the stem lineage leading to birds. But we don't really know where characteristic features of avian physiology first appeared. And people have made many arguments based on bone histology and estimates of growth rates. And some people who work in these areas tend to make sort of very unequivocal statements. We know that dinosaurs were bird-like endothermic homeotherms. But then some other people tend to make very definitive statements where we know that dinosaurs must have been warm because they grew very quickly, but we don't know if they really regulated their body temperature around a fixed set point. And this is just one paper that looked at those patterns recently, and you can kind of, maybe you can see like the dinosaur points are grey points here, and the issue is for smaller dinosaurs tend to have mass-specific growth rates comparable to living ectotherms. Larger ones really have mass-specific growth rates comparable to living endotherms. And you can fit a regression line to all those dinosaur points, and really what you're doing is assuming things like all dinosaurs have the same temperature, and the scaling of growth rate with body mass must be somehow fixed by thermal metabolism, and I would say those things are far from certain. So ideally we'd try and use some other data that we believe might be able to tell us something about dinosaur physiology. Few of our conclusions are likely to be concrete. So we wanted to know the masses of lots of dinosaurs. Now, if you want to know the masses of lots of animals today, you can weigh them, and this elephant is very obligingly standing on a set of jumbo scales. It's much harder to do that with a dinosaur. Not just because they don't walk onto the scales. I mean, I could put scales in front of this dinosaur and walk onto them, but also mainly it's missing most of its original body mass, and it's highly mineralized, and obviously it's very difficult to know the mass. One way you might know that we could consider to be very reliable is we could make a 3D scan of the skeleton, and we could sort of estimate a convex hull around the skeleton that looks a bit like the animal before, and we might have some idea of density. We might argue over that because some people think this dinosaur had a lot more air in it than others do. But we might come up with reasonable ranges of mass estimates for individual specimens that are very complete that way. It would be very difficult for us to do a macroevolutionary study that way because most dinosaurs are very incomplete. So my colleagues Nick Campione and Dave Evans have sort of systematically measured aspects of the limbs, primarily of lots of living animals with a variety of different stances from various different parts of the vertebrate tree. And the question they wanted to ask was, for these animals that have known living masses, what kinds of measurements could I best use to predict those masses, and is that relationship, does it vary prominently with variation in things like stance, or does it contain a strong phylogenetic signal? And surprisingly, I think to many people, the answer seems to be that it doesn't vary substantially with stance or phylogenetically. And so there's a sort of relationship that seems to be constrained by the physical laws of the universe, where if I measure the circumferences of the mass supporting limb bone shafts, that could provide me with a prediction of mass that's likely to be correct to within a sort of order of 2 times. So you might have half the actual mass, or you might have twice the actual mass, but you're going to be in the right order of magnitude for many animals, and maybe sometimes that's good enough. The advantage of this, many of our dinosaurs are incomplete, but we could still predict a sort of central tendency of mass for those animals. So we estimated the mass. We wanted to estimate the mass of all dinosaurs, but it's not possible, so we only estimated the masses at present of about 600 of them, and the patterns look kind of broadly like this. I mean, this is a bunch of data points for dinosaur masses through time. So these are the masses of the largest mammals that lived. So it's actually interesting, most dinosaurs are actually about the size of many mammals. Actually, many mammals, probably more than 75% of living mammals weighed less than a kilogram. One of the interesting questions about dinosaurs potentially is not why were they so big, it's actually why were they never very small? But I'm going to be interested in the absolute biggest dinosaurs, because maybe we'd expect extremes to show the most kind of prominent relationships. Ancestral dinosaurs and the primitive members of most groups weighed about 30 to 50 kilos. Seems like a very unequivocal pattern that comes out of that data. And maximum size increased over an interval of more than sort of 50 million years in the late Triassic and Jurassic. we can't really use data from that interval if we're interested in patterns of maximum size, because at that time we don't expect patterns to be driven by climate, we expect them to be driven by evolutionary change. But once we get into a kind of maximum size quasi-equilibrium in the late Jurassic and Cretaceous, we might be able to say those patterns, if they're going to be controlled by physical environmental variation, that's the time that they would be. We also use databases of sort of geochemical isotopic variables for paleotemperate latitudes. The reason we did that is almost all dinosaur fossils are from paleotemperate latitudes. And the one I'm going to focus on is delta O18, which is sort of paleotemperature proxy. These other things capture various other aspects of the Earth system, and it's interesting that they don't explain variance in dinosaur body size change very well, which suggests we're not looking at some combined Earth system function. If we find answers, it might be that temperature is just very important. So these are the biggest dinosaurs, sauropods, so their sort of body sizes plotted onto time. This is the hottest interval of the Mesozoic, the early Turonian thermal maximum. You really do find the absolute biggest dinosaurs at that time. There's only one data point here, but Argentinian people keep reporting new gigantic dinosaurs weighing 70 or 80 tons in the BBC recently, so I think that's not really a single outlier in the future. This is a time about which we know almost nothing about sauropod evolution. I think that's quite striking. But these are really the times sauropods attain their maximum body sizes in the late Jurassic and during the early Turonian. And this is our pattern of like delta O18 oxygen isotope. It's inverted, so increases in this line correspond to generally higher temperate latitude temperatures. And I can statistically interrogate the relationship between these things in various ways. Like we might be interested in the maximum body size or the median body size. We might try and capture the pattern of temperature change using a lowest line or using weighted means. It's not clear to me what the single absolute best way to do it is. We might ask the question using a phylogeny. You can do it all those different ways, and you basically find that temperature change explains between 0.2 and 0.8 of the variance in sauropod body size evolution, which I believe is quite a lot, given that we probably expect our data to be relatively hairy for a group like this that isn't exceptionally well sampled, like an invertebrate group. We can plot our data so that size of points corresponds to body size, and latitude goes up and down the plot and go through time in this direction. And you can just sort of broadly see some of these patterns occur simultaneously in both hemispheres. We have our biggest northern hemisphere dinosaurs at the same time as we have our biggest southern hemisphere dinosaurs. And we can analyze our data for individual hemispheres, and we just keep finding the same answer over and over again. So we can say sauropods were bigger when it's hotter, which is the opposite of mammals. I personally find it hard to reconcile that with the idea that they're strictly sort of bird-like homeotherms. But there are other potential explanations. It might be that resource gradients are more important in determining dinosaur size in the Mesozoic, and it might be that hotter intervals have greater primary productivity. We don't actually know whether that's true yet. I would like to know in order to test that hypothesis further. Just look very briefly at other dinosaur groups. Ornithischian dinosaurs, whose latitude is going along the x-axis through time. Several different groups attain large body size at different intervals, and those aren't the intervals at which global temperatures were highest. You actually don't find a statistical correspondence of any kind between ornithischian size and global temperature, though, so it's not really a negative correlation. They don't really show the mammal-like pattern. The reason for that seems to be that their patterns of body size evolution are dominated by independent evolutionary origins of large size. So stegosaurs evolve very large size in the middle and late Jurassic, and you have, until they go extinct, you have some ornithischian maxima achieved. Different types of ornithopods achieve large body sizes evolutionarily independently at different times, and ceratopsian dinosaurs as well in the late Cretaceous. So actually, when evolution is very important, it's very difficult to test temporal patterns, but it might be easy to test spatial patterns. So we try to look at these patterns in space in the late Cretaceous of North America, where we have a lot of data for these groups. And theropod dinosaurs also show no correspondence. You can kind of see when you look at these distributions of data points, maybe we should be very skeptical about patterns in latitude that are commonly held for Mesozoic tetrapods, because there are actually few intervals for which we have a broad latitudinal span of data points. But I don't like to be too pessimistic about it. So in summary, body size of sauropods, the largest dinosaurs, actually the largest terrestrial animals that ever lived, is positively correlated with temperature proxies. It's nice. Sauropod body size clearly wasn't thermally limited. Some people say mammalian body sizes are limited by temperature. In fact, Sauropod seem to have been able to be bigger when it's hotter. That's the opposite of being thermally limited. It doesn't matter how good you are at dumping heat. You have to explain a positive correspondence. Why is it that they could grow bigger when it's hotter? And I feel it's difficult to reconcile with mammal-like homeothermy, but I don't think that's really a sort of slam dunk interpretation of the data because, several candidate explanations exist, and we'd probably like to know more about the distribution of productivity and other climatic variables. And these are my acknowledgements.